Okay, so today we're going to talk Doppler effect, and this is actually more of a physics phenomenon that I'm sure you're aware of. You've all heard the Doppler effect before. Maybe you didn't know this is what it was called, but you probably heard this. And so I'd like to actually start by playing a short little YouTube clip, if I can find it down here. Yeah, I guess I can go full screen. And so this is a fire engine that's demonstrating the Doppler effect. We'll just listen a few times here. The video really doesn't matter. It's the sound that matters. So for those of you who are like musically inclined and you know the word I'm going to talk about is pitch. Anybody know the word pitch in a musical context? A high pitch is up high and a low pitch is down low, right? Pitch is frequency. Like from a physics point of view, if you have a really high note, it's a high frequency. If you have a low note, it's a low frequency. What happened to the pitch of the fire truck as it went by? It dropped. Now, the siren itself was always doing the same two notes back and forth. Da, 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 da. The siren itself didn't change. But as the fire truck drove by, we heard something different, and that's called the Doppler effect. I'll play it one more time, and then I'll explain the theory again here. So we don't need to watch the whole thing, but so da 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 da. And now it's lower. So my goal today is basically to describe how this physics phenomenon works, and then we're going to do a formula on it in a bit. So I'm going to use this slide to describe how this formula works, and maybe you've already figured it out based on the pictures. Before I do that, though, I need to just recap something we learned about earlier in waves. Okay. One of the ways that we draw a wave is up and down. Okay. This is a transverse wave. It goes up and down, back and forth like this. But we were hearing that. That's a sound wave. Sound waves are actually longitudinal, and longitudinal waves work more like this. There's like a compression of particles, then there's like an open section, then there's another compression of particles, a compression of particles, a compression of particles, and it's more like this, it's more like pulses. That's what we're actually hearing when you're hearing noise, right? We've talked about this before. When I'm talking to you, air molecules are not going from me to you. But air molecules from my voice are causing that air to vibrate, which causes the air next to it to vibrate, causing the air next to it to vibrate, and through a domino effect, eventually the wave passes. This is how we try to visualize it. So nothing actually moves up and down. It's more of a pulse. Okay? However, when we want to draw it in 3 dimensions, we draw a wave front, where if this is me right here yelling at the class, hey, listen up, the waves, we saw sometimes draw them in circles like this. This isn't me falling down like a black hole or anything. This is just waves emanating outwards. And so this would mean that this is a wave that went up and down and up and down and up and down, and that's one way we represent it. But when I talk, I don't have to talk just to you, because like when I talk in one direction, sound goes all directions, right? So sound is also going out this way, and sound is also going out this way, and so we use these circles to try to represent sound going out in all directions. Pretty good with that so far? Well, what happens if the source is moving? What if this ambulance right here is supposed to be giving off sound in 360 degrees directions, but what if the ambulance is moving? And the analogy I gave earlier today, and it seemed to work, so I'll do it again, is imagine that I wanted to throw a whiteboard marker. So when one walks in the door, I throw a whiteboard marker. Actually, out the door this time. But what happens if I was in motion as I was throwing the whiteboard marker? What if I tried to catch up to it again? Now, I mean, I'm going to throw the whiteboard marker far enough that I can't catch up to it. But I don't know if you guys can even see. The whiteboard marker that I ran to is about this far away. Whereas if I didn't run to catch up to the whiteboard marker, wouldn't it be further away if I didn't run to try to catch up to it? Now, in theory, like an ambulance or a fire truck that's giving off a signal, it's not going to catch up to the sound wave that it's giving off. Sound moves way too fast for that. But it's kind of catching up. In the same way that I throw the pencil, I try to follow it. Right? That's what's happening right here, is that this ambulance right here, it's trying to catch up to its sound waves. And what ends up happening is they actually get compressed. They get a shorter distance in between them because the ambulance is catching its own waves. Anybody know the speed of sound? Yeah. 330 meters per second. 330 meters per second. You're close. You're just, yeah, wrong units there. Yeah, so 330 meters per second is about how fast that sound travels. So unless this ambulance is driving ridiculously fast, I mean, is it ever going to actually catch its own sound? No. Anybody ever heard of a sonic boom? Or you've heard of like Mach 1 or Mach 2 or Mach 3? Ever heard of that before? So a sonic boom occurs when you hit, I believe, Mach 1, which is when you're actually traveling the speed of sound. What ends up happening is an airplane, like a jet fighter, might actually fly so fast that it's traveling faster than the sound itself produces. So maybe a different example. You know how lightning, how you see the flash of lightning, and then a few seconds later you hear the cry, rumble kind of thing there? Well, it's kind of like that. If you could actually travel fast enough in a jet fighter, you might actually outpace your own sound, and then later the sound hits you. Okay? Well, okay, unless you're actually traveling at Mach 1 or Mach 2, that's not going to happen. So what's happening in this case here is that this ambulance is giving off sound in all directions, but it's trying to catch up to its own sound because it's in motion. What ends up happening here is that it's catching up to some of its own waves, and those waves are then compressing on themselves and becoming shorter. Now, what we know about music is that short wavelengths have high frequency, and high frequency is a higher pitch. So for any of you who do music and you play like notes on an instrument, D is higher than C, right? And so therefore there's now a new pitch, the pitch goes up. The same thing happens though as it's leaving. In this example here, as the ambulance is leaving, the scenario would go like this. I'm going to send off a wave, and again, the wave in this example is going to be throwing the pen. But now I'm going to go this way. So I'm not trying to catch my own wave, I'm actually going the opposite direction of it. What happens is the wave lengthens instead. And so if you're looking at that same ambulance right here, as those waves are going back to the person to hear them, this person right here is hearing waves that are further apart because the ambulance is driving away from you. What we know about further apart waves have a longer wavelength. And when things have a longer wavelength, they have less frequency. And less frequency means a lower note. So this explains why when the ambulance is coming towards you, there is a high frequency, but when the ambulance is driving away from you, there is a low frequency. So I'll just play the video one more time just to re-illustrate the point. Oh, actually, one more thing before I play the video. What happens if the ambulance is basically right next to you? I mean, not hitting this person, obviously, but like, say they're right next to them. Would you hear the pitch being higher or lower? Well, you're probably just going to hear what its normal pitch would be, right? So normally the ambulance would be da-da-da-da-da-da, but if it's driving towards you, it's actually da-da-da-da-da-da. And when it's driving away from you, it's da-da-da-da, it's lower, right? So what you might even hear in this video, let's try to listen to 3 different pitches. Listen for a high pitch as it's coming towards you. Listen for a middle pitch for literally like 1 second as the ambulance is right next to you. And then listen for a lower pitch as it's driving away. So let's run that video again here. So high to begin with. As you see the fire truck drive by, then you'll see the middle and then the low. So for those of you who are musically inclined, I don't know whether you kind of heard the same thing I did, but it was high, low, high, low, high, low, high, low. Then it kind of went into like a middle sort of range, and then it dropped down to the lower range, right? We heard the middle range because that's what its actual frequency is. That's the actual pitch of the ambulance. Okay, let me show you a couple of more pictures and examples, but hopefully I'm explaining this well. I like this animation. This little animation at the top kind of illustrates the same concept. At first, you're going to see the car, and the car is producing a sound, I guess, right? But as the car drives into its own sound waves, the waves get compressed. Right? If you're kind of wondering, well, like, how can those waves get compressed? Well, because it's trying to catch up to its own wave. And as it catches up to its own waves, it's giving off more and more waves. And so they get compressed over here on this side. Right? But now look on the reverse side. Look at this side over here. They actually are pretty far apart over here. So as you're driving towards something, wavelengths get squished, higher frequency. As you're driving away from something, wavelengths get pulled out, lower frequency. I got one more picture here that kind of illustrates the same thing, but have I more or less explained this? Any questions on that so far? Now, we're going to do a math formula in a second, but before I get to that, I want to kind of do a brief aside. We can actually see the Doppler effect. They were physics demonstrations. Thank you. Wondering why the pens are outside the door. We can actually see the Doppler effect in more than just sound waves, because sound is one type of wave, but light is another type of wave. And we've actually recognized what's called the Doppler shift in our universe. Scientists believe that the universe is expanding. I don't know if you've ever heard this before, but we believe that we have what's called an inflationary universe. It's constantly getting bigger. It actually grew from what's called a singularity. And we believe that a big bang basically caused an explosion, and the universe has been growing bigger and bigger ever since. I don't know if you've ever heard that theory before. And the evidence that scientists have that there's an expanding universe is something known as a red and blue shift. When scientists look at faraway galaxies in their telescopes, most of the faraway galaxies look slightly red. And that's not because they're emitting red light, but because as things move further away, remember how we talked when things move further away, the wavelengths get pulled out? But when wavelengths move towards you, they shrink. Well, red is the furthest wavelength that we can visibly see. Red is the farthest, longest wavelength light that we have. Whereas blue is light that's squished together a little bit more. Now, I mean, it's not that, like, I'm exaggerating in this photo, right? Like, this photo is not what the actual wavelengths are, but they're exaggerated. What this means then is that when scientists see faraway galaxies that look slightly red, we believe that they are actually moving outwards and away from us, right? Now, here's the weird thing. If we started seeing them becoming blue, it means that they'd be coming towards us. One of the kids in the last class pointed something out to me that I need to look into more. But pictures of the Andromeda galaxy are apparently blue, which would then explain why we believe that the Milky Way galaxy and the Andromeda galaxy will eventually collide, because apparently it's a galaxy that's coming towards us, and we can tell that by the blue wavelength. I need to look into that more, but that was a great idea that she had. So, while I'm on this topic, because I like talking about this, the field that I'm discussing is a field of physics called cosmology, and it basically discusses like what our universe is going to do in the future, where it came from. It answers like really big picture things. You guys know who Stephen Hawking was? The guy in the wheelchair? Right, he was a cosmologist, and one of his goals was to figure out like, well, where did the universe come from and how will it one day end? And most physicists are on the same line. They believe in a big bang that exploded and caused the universe to expand. There's actually two main thoughts about how the universe will end. One of them is that the universe will continue to expand, just getting further and further apart, getting bigger and bigger. But if the universe continues to expand in volume but only has so much energy, eventually we would freeze. I mean, not, tomorrow, but in the future, if the universe doubled in size but there was only the same amount of energy, we would feel colder relatively. Does that make sense? And so we believe that the universe might end due to what's called a big chill. The other theory is that maybe gravity will take over. You know how gravity is supposed to pull everything particle-wise together, right? If you have matter and something else has matter, there's a gravitational force of attraction. Physicists believe that maybe after the Big Bang is done and it's inflated the balloon to as big as it gets, maybe it'll actually shrink back down again and gravity will make everything come back together at a singularity again. And it'll basically go in reverse of what the Big Bang would have been. So we would know that then based on these shifts. If we see galaxies that are slightly red, we believe they're moving away from us. Galaxies that are slightly blue mean they're moving towards us. Either that or our instruments are wrong, or maybe the galaxies themselves are somehow red, but it's explainable by red and blue shift. So, anyone ever heard that before? Kind of cool stuff. So, anyways, the point I wanted to make on this slide here is that the Doppler effect is not just for sound, but also for light. We can actually see light change colors on us. Okay, here's our formula. So the formula we're going to learn goes like this. It's F equals V over V plus or minus Vs Fs. And I'm going to go over how to use this formula in a second. But what I think both of the last two classes found useful is I'd like to maybe pause for a second on the Doppler effect, and let's discuss all of the formulas that you've learned this unit. So I'm going to add that formula to the list, but maybe just as a brief aside, let's do a quick recap of all the formulas we've learned. There are three main sections to our most recent unit. We've talked about things that oscillate, we've talked about things that go in circles, and we've talked about waves. Okay. I just want to quick categorize all the formulas, because you have to use them in the right location. Here's an example of an oscillating formula. T equals 2 pi root L over G. That is an example of a formula that you can use for something that oscillates back and forth. Be specific, though. What is the object that has to oscillate back and forth in that formula? Can it be any object? What object is going back and forth in this particular formula here? A pendulum. There you go. You got it. Pendulum. Yeah. Now, there is a second formula for things that oscillate back and forth that you can use. it's t equals 2 pi root m over k. What is that a formula for? Again, it goes back and forth, but it's not a pendulum anymore. A spring, yeah. A couple of good examples would be a trampoline bouncing up and down. There was an example on one of my tests, if you've tried it, of a bungee jumper bouncing up and down. So these are formulas right here that we've learned about. It's been a while because they were back in the first couple days of the unit, but they only ever apply if it's oscillating back and forth. You cannot use these formulas on waves. You cannot use these formulas on things that go in circles. Okay, it has to be in the right locations. Then we learned about some formulas that apply to circular motion. Here's one. The velocity of anything going in a circle is equal to 2 pi r over t. There's one formula. Acceleration of something going in a circle is v squared over r. And a third formula that hopefully you're somewhat familiar with is 4 pi squared r over t squared. These are formulas for things that are going in circles. But again, they only apply to things going in circles. If you have a pendulum, you cannot use these formulas. I find that that's one of the biggest struggles kids have at this point in physics, is that now that we're opening up the formula sheet and we've used many of them, right? Like if you were to look at your formula sheet, we've covered maybe half, maybe a third, somewhere between a third and a half of the formulas. You got to know when to use the right formulas. One more thought on circular motion. Circular motion is also common to need to build a formula. And when I mean build a formula, this is where you do something like F net equals MA, but it's actually FC because we're going in a circle, so that's MAC, which is really MV squared over R. But your net force is the force of gravity minus the force of friction. You know how we had to like build formulas? That's just a random made-up example. And we did a whole lab on this, but it's very common you have to make your own formulas in circular motion. Okay. Again, but that only applies to something going in a circle. So don't try to build a formula using F net for something that's oscillating back and forth. It's not the right scenario. Okay. The third part of our unit has been waves. And in waves, we've already learned one formula, V equals frequency times wavelength. Okay. The final formula is the one we're going to talk about. That's today's formula. It's that frequency is equal to velocity over velocity plus or minus velocity times frequency. And so we'll talk about how to use this formula in a second. But I thought this was a good representation so that you only use the right formula in the right scenario. Because sometimes you get overwhelmed at times with like all the stuff that's happening. So. Okay, one more thought. Although I'm trying to put these into columns and saying you can only use the formula in the right time, there is actually one more formula I haven't discussed. What is the common thread? What is the common theme that everything that oscillates goes in a circle and has a wave? What do they all have in common? Period. You got it. Yeah, they all have a period or a frequency, right? And so if I could make one more box here, what is in common that you can use in any scenario is that a period is equal to the reciprocal of a frequency, or the frequency is equal to the reciprocal of a period. This is what is in common. You can use that in any single scenario. And that's why I put this unit together. Some teachers, they do it in 3 different units. Some teachers, they do 2 of them together. But I thought these 3 things, they all go together because the commonality is that they all are repetitive. They all have frequencies and periods. But you have to use them in slightly different ways. So as you're beginning to solve problems, it may be useful for you to now categorize your questions as to, is this oscillating, is it circular, or is it a wave? Because that'll help narrow down what you need to do. You get what I'm saying? Sometimes it's overwhelming and you're like, Chris, I've got like 14 formulas to look through, or 17 or 24 formulas to look through, and you're not really sure which ones to use. This might narrow it down a bit. So, okay, anyways, that was a brief aside. Let's go back to this formula here. So this is our last formula in the section. And the way this formula works is that this F over here is your apparent frequency. It is the frequency that you hear. Frequency you hear because it's in motion. Whereas this F over here is the frequency, oh goodness, I can't spell there, you would hear if it was stationary. Okay. So there's two frequencies in this formula. The frequency on the far left-hand side here is the frequency you're hearing, which is an altered frequency. It's either too high or it's too low. Neither of them are actually the correct frequency. If it was just standing still, the frequency in the middle would be the stationary frequency. Okay. And what this stuff in brackets right here does is it alters that frequency. This stuff in brackets will either make that frequency go up or down, depending on whether it's going away or towards. And because of that, that's why there's a plus or minus sign inside of here. Because the plus or minus sign accounts for the fact that sometimes you're going towards, and if you're going towards, your frequency increases. Or if you're going away from something, your frequency decreases. I'd like to explain how this middle section here works. The V that you have right here stands for the speed of sound, which is 330 meters per second. So both of these V's right here are 330 meters per second. The final variable in this formula, Vs, is the velocity of your source, and it's the thing that is moving. So if you have an object that is moving, like say the ambulance, if the ambulance is traveling 50 kilometers an hour, that's what this number right here is. It's the speed of the object that's in motion. Okay. Now here's how this formula works. I'm just going to change out these numbers for easier numbers. Let's say that the velocity was 10, and let's say that we added 2. So let's say the speed of sound was 10, and the object was moving 2. Well, what would happen is you'd now get 10 over 12. 10 over 12 is a fraction that would reduce your frequency. So this would be for the scenario when you want your frequency to get smaller. When do frequencies get smaller? When you're moving away. So if things are moving away, you get a lower frequency. So therefore you use the plus sign. But if you did 10 over 10 minus 2, see how that would give you 10 over 8? Isn't 10 over 8 going to make your number bigger? And so this would then give you a frequency that is higher, and you get a frequency that is higher when something is moving towards you. So long story short, I need for you guys to be able to identify whether or not to use the plus or the minus sign. What we found as a useful trick is that if you want to increase your frequency, use a minus sign. If you want to decrease your frequency, use a plus sign. So like it's the opposite. If you want a frequency to go up, use a minus. If you want your frequency to go down, use a plus. So let's try an example. Here's basically the exact scenario we just watched on YouTube video. Say there's an ambulance, and the ambulance has a frequency of 8,000 hertz, which is ridiculously high. And the ambulance is traveling 28 meters per second. What would you hear as the difference between pitches if the speed of sound is 330? By the way, this was a good talking point earlier today. Is the speed of sound always 330 meters per second? Actually, it's not. It depends on different factors. Because how does sound move again? Sound is moved by the vibration of molecules. Okay? What if those molecules are damp because it's wet outside? What if there's a high humidity factor? High humidity might dampen your speed of sound. Does that make sense? Or what if it's really hot outside? Temperature could actually increase your speed of sound. So the 330 is not a hard number. It can actually be like 333 or 329. It really depends on temperature, pressure, humidity, because those things will affect how fast the molecules themselves can vibrate. Does that make sense? Like today, I don't think the speed of sound is going to be quite as fast, right? Because it's very wet outside. There's more water vapor in the air. Water vapor is more of a heavier gas than carbon dioxide or than hydrogen or nitrogen. And because of that, the molecules won't vibrate quite as fast as normal due to high humidity. Anyways, let's try our example. F equals V over V plus or minus Vs, and all of that gets times by Fs. So let's plug in some values. We know that the velocity, we're going to go with 330. Just recognize that it's not always 330 exactly. Okay, I'm going to add 28. And then I'm going to times all this by 8,000. Now, what I like to do to help show students is I'm just going to find just what's in the fraction. So I'm actually going to skip the 8,000 just temporarily and just show you what the fraction is going to do to it. If I do 330 divided by 330 plus 28, my fraction is 0.92. I will then take 0.92 times by 8,000. And I'm going to get a frequency of 7374 hertz. What happened to the frequency? Went up or down? Down. Why did it go down? Was this thing moving away or towards? Frequencies go down when things move away. Okay. So there we go. The frequency dropped when we moved away, which is why you heard the siren going on the low end of the spectrum as the ambulance passed you. Well, let's try it again, but now let's make one subtle change. Let's just change this from being a plus sign to a minus sign. So do 330 over 330 minus 28, times it all by 8,000. So 330 divided by 330 minus 28. My fractional number right here is actually 1.09 times 8,000. This should then make my frequency increase. So now we're going to have a frequency of 8742 if I round it hertz. And so this would be the frequency as it's coming towards you. So again, if you know how frequency relates to pitch, this is a high pitch, so therefore it was up da 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 da, and then it's eventually going to drop down to da 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 da, and it's going to drop its pitch, right? That makes sense? No questions? Okay, let's try example 2. So example 2 I devised to help us practice our algebra skills, because the formula itself is pretty easy if you're solving for the frequency on the one side. But what if you're not solving for the frequency? What if I give you two frequencies and ask you to solve for a different variable? Here's kind of a silly scenario, but imagine there's a singer, and the singer needs to sing an A, and A is 880 hertz. But the singer is flat. For those of you who know anything about music, when you're singing flat, you're a little bit low on your pitch. And so they're hitting an A flat, which is 830 hertz only. Now, maybe just for whatever reason, the singer has a sore throat, and they can't actually sing an A. They can only hit an A flat. You know what they could do? They could run really fast. And they could try to catch up to their own sound waves. This would be ridiculous. But in theory, you could sing and run. And if you were running into your own sound waves, it would make the pitch go higher. Ridiculous, because you'd have to run really fast. But that's basically my silly question is, how fast and in what direction would the singer need to be moving to make their A flat turn into an A? If I were to give a picture here, right, where's the first one here? Right here. So here he's given off an A flat. And now that he runs into his own sound waves, they squish, and it's now an A. Right? And you raise the pitch up a little bit. So first question, actually, which way would you need to run? Would you need to run towards your sound waves or away from them? Towards, right? Because if you want to raise the pitch, you need to run towards. So now here's what makes the formula kind of tricky, is that if I rewrite it out again here, F equals V over V plus or minus Vs, all times by frequency S. We're actually being asked to solve for this variable right here, the velocity. Sorry, those are on the floor because I was throwing them for an experiment. Yeah, we use pens to throw for experiments. So we're actually being asked to solve for the velocity of the source because we've got to figure out how fast you have to run to get there. So let me walk you through the algebra for this one. This worked well twice, so I'm going to do it again. You have to bear with me. I'm going to use different colors for every single variable here just because it worked well last time. So we need to algebraically manipulate this equation to solve for the pink Vs right here. I'm going to do one more thing. What sign should go between them, a plus or a minus sign? If we need to raise the pitch, we need to use a minus sign because it's the opposite. Okay, so there's a minus sign. Okay, so let's talk algebra skills. If we want to get the pink Vs by itself, isolated, first of all, it's in the numerator. You guys know what I mean when I say numerator. Or, sorry, it's not in the numerator. It's in the denominator. And we need it in the numerator. So what I'm going to do is I'm going to take both of these terms off the bottom of the fraction, both of them, and I'm going to have to bring them up to the top of this side over here. Right? What I'm doing is I'm cross-multiplying. I'm taking both of these two terms, and they're stuck together, aren't they? Right? Because they're being separated by a minus sign, they're stuck together. I'm going to bring them over to this side over here. Well, maybe I should bring the f down to the bottom of that side. See how I'm like cross-multiplying and dividing? The next problem I have, though, is that there's still this blue V next to it right here. I want to have the pink Vs on its own. Maybe I should move it a little further over there. But there's this V that's still sitting on this side here. So I know I brought the V up to the side here, but now I need to bring it to the other side. And to bring it over to this side over here, you're going to have to minus it. And the reason you have to minus it is that when it was over on this side here, it was really plus V minus Vs. I know there's a minus between the two of them there, but the Vs is what's negative. The V was actually positive, so to get rid of a positive V, you have to subtract V from both sides and bring that over there. The last problem you have is that there's still a negative sign in front of this Vs right here. So here's what I'm going to do. I'm just going to ignore the negative I get when I'm done. When I solve this equation, I'm going to get a negative number, and I'm just going to make it positive. So let's plug in some values. This velocity, speed of sound, 330. This frequency is the frequency that we would like to hear. We would like to hear 880. This frequency right here is what she actually sings. She's actually singing 830.6. And then this velocity is, again, the speed of sound. So I'm going to solve that. 330 divided by 880 times by 830.6, and then minusing 330. And I'm going to get a negative number when I'm done. I got negative 18.525. But that's what negative Vs is equal to. So just kind of ignore the negatives. What speed do you need to travel? That's in meters per second. Oh, I didn't write that very well. There we go. Meters per second. If you can run basically 18 meters per second, you could catch up to your own sound waves and make it go up a semitone if you know how that music works. Which is ridiculous, because I don't think anyone's going to be able to run 18 meters per second. But this does lead back to that conversation I had about like Mach 1, Mach 2. If you're traveling the speed of sound, in theory, you are traveling exactly as fast as your own sound waves are coming off of you. And so if I were to talk and run, if I'm running at Mach 1, basically I would arrive exactly as your sound arrives. Planes that can break the speed barrier, basically they go past you, and then you hear the boom. That's where the sonic boom comes from, if you ever heard that before. So you'll actually hear the plane after it passes you, because sound has to catch up. But that's only if they're traveling fast enough. Okay, questions on this example. It's kind of ridiculous, but it was meant to help you practice algebra. Anyone have any questions you want to ask? Okay, we got one last example. The final example I want to discuss here is about musical instruments again. And I brought a couple of these boom whackers from home to help kind of illustrate the point. I'm just going to close the door here, because I'm going to hit these on the desk. For those of you who know instruments, this right here would be having a lower sound than this one right here. And the reason why is that this is going to have a lower frequency than this one. This is going to have a high frequency, this is going to have a low frequency. Can you guys tell that this one's the low one and this one's the high one? And one of the reasons we know that is this picture up here. I'll go back to my desk with the writing pad now. The way that an open column instrument works, if you watched my video from yesterday, is that sound waves need to bounce around inside of your instrument. Whatever instrument it is, a tuba, even if you pluck a guitar string, sound waves are bouncing back and forth at a fundamental frequency. And you need to have it go from antinode to node to antinode. It has to be open on both sides for this thing to bounce around properly inside. And the way the math works is that the length of your instrument is basically always, it's half of your wavelength. Okay? You can fit half of a wavelength in here. This is a wavelength going down, but that's only half of it, because the other half would in theory come back up again. But it doesn't come back up again, it actually bounces back to itself. So the wave would go down. In theory, it would like to keep going, but because it meets this open container, it kind of reflects and it bounces right back to itself. And so it's like it's symmetrical. So you need half of a wavelength for the length there. So if I tell you that you have a flute that is 0.60 meters long, it means that the wavelength of sound that it produces is 1.2 meters, because I'm doubling it. Okay. If you can kind of picture that, imagine that this thing right here is 60 centimeters across. The wave that goes through it would want to start up here. It would want to go through the node and down to the bottom. And then in theory, it would want to come back up. It would want to go down and back up. But it doesn't. It goes all the way down, and then it reflects back up to its original starting point, and it goes back and forth like this. And then the other half of the wave goes up like this. You guys remember when I had that spring across the room and we kind of vibrated it up and down? I was making what's called the standing wave, and that's more or less what this picture right here shows you, is the standing waves that are vibrating up and down. Okay. Long and short of this is that the longer the instrument, the longer the wave you can have. the shorter the instrument, the shorter the wave. Well, short waves mean high frequency. So what that really means is that a long instrument has a low pitch, and a short instrument has a high pitch. You guys do music-y type stuff like this, right? Like one of the highest instruments there is a flute. A flute is like this big, which is why it makes such a high noise, right? Whereas if you had like a big bassoon or a tuba has all sorts of like wrapped coils inside of it to make it really long. It may not be in a straight row, right? But a tuba has a really long length to it. That's why a tuba is such a low instrument, right? It's all based on the length of the column. So anyways, let's start here. I've already answered 1A. What is the wavelength of the longest standing wave the flute can produce? 1.2 meters. All you have to understand is that if you have an open column, you just times it by 2. That's it. Okay, it was in our notes from yesterday, so hopefully you watched that. Okay. Well, for part B, if I wanted to ask you the pitch or frequency that the flute could make, here's how I do that. The formula for waves, there's only 2. Right? Remember that slide I did earlier? Go back to all those formulas that we have. Where were they? They were here. All these formulas that are right here. If you're trying to figure out what formula to use, none of these formulas fit. None of these formulas fit. It's got to be one of these 2. If I want to ask you what frequency that a flute can play, this top formula would work pretty well. Velocity is frequency times wavelength. So the formula is velocity is frequency times wavelength. I want to know the frequency, which is the pitch that the instrument can play. So I'm going to take velocity divided by wavelength. What speed is the wave traveling? Speed of sound, because it's making sound. Right? So the speed of sound is 330 meters per second. How big was that wavelength that we could fit inside the tube? Keep in mind, we only fit half the wavelength inside the tube, right? But how big would the wavelength have been? 1.2. So this will tell you your frequency. 330 divided by 1.2 gives you a frequency of 275 hertz. Now, that is the lowest note that this instrument could play. And the reason why it's the lowest note this instrument could play is because we can increase the frequency. Now, not by running with your instrument. That's kind of silly. But what do other instruments have on them to change the notes? Well, they've got little buttons and valves, and like a trombone's a good example. You know how a trombone, you like slide it in and out, right? If you were to shorten the instrument up, it would change the pitch. And so I'm actually going to go out of order. I want to talk about letter D next. It says, if keys on the flute were pressed to shorten the length of the column, what would happen to your pitch? Your pitch would go up. Because we know that as you shorten up the column, it means that your wavelength is shorter, which means that you have a higher frequency, which means you have a higher pitch. So if I go back to my boom whackers again, which one of these is going to make a lower sound? The bigger one, because there's a bigger wave inside of it. A bigger wave has a low frequency. This has a smaller wave. Smaller waves have higher frequencies. So low, well, relatively low. There's low, and there we go. I got to hit it the right way. I'm actually getting a double vibration in this one right now because it's actually the same pitch. Let's try that again. There we go. You guys can hear the difference there? If I hit it right here on the edge, I think I actually got the same frequency. These are actually both letters. They're both the note C, if you guys know much about music. And it's actually exactly double the size there. And so if I hit it right, I might actually get a double wave. Can you see how you can actually get more than one wave inside there? If I hit it right, maybe it'll sound the same pitch. So I can actually make this play different pitches depending on how I hit it. Anyways. Okay, so we now know what note, the lowest note that this flute can play is. Now, this is kind of another silly example, but it's actually a common problem. Say that there was a parade, and there was a band playing on the back of a flatbed truck in a parade, and the parade was then carrying the instrumentalists through the streets of the city. The Doppler effect would happen. And in theory, what would happen is the instruments would sound out of tune, not because they're not tuned properly, not because the musicians suck, but just because they're moving, right? And it won't be a lot, but the instruments would actually sound flat or sharp, right? Now, the musicians would never know, because the musicians are also on the truck, and so they wouldn't know the difference, right? But people who are standing on the sidelines, hearing the truck come towards them, the instruments would either sound sharp or flat, depending on whether it's coming towards or away. So that's why I want to just practice for number C here, is what would the frequency actually sound like to a stationary observer if a truck is departing away? So let's just practice the Doppler one more time. The formula for that was frequency equals V over V plus or minus Vs times by Fs. But I can't leave it as plus or minus though, right? Because it's got to be one or the other. Should be a plus or a minus. What's going to happen to the sound as the truck goes away from you? The truck goes away from you, did we get higher or lower sounds? We got lower sounds. And if you want to drop the frequency, it means you need to use a positive sound. So every time you use the stupid Doppler formula, you have to figure out whether you're using a positive or a negative. Okay. Now I can plug in some values. Oh, I got to do one more thing though. This 10 kilometers an hour is not in meters per second. I got to convert it to meters per second. If I haven't shown you guys this trick yet before, just divide by 3.6. You get 2.7 repeating meters per second. And if I haven't shown you the trick, here's the logic behind it. I'll do it down here. In 1 hour, there are 3,600 seconds. And in 1 kilometer, there's 1,000 meters. Well, 3,600 divided by 10,000, the ratio of it is 3.6. So you're always either making it 3.6 times bigger or smaller, depending on which way you're going. So that's just a little shortcut. Okay. Velocity, speed of sound, 330. Other velocity, speed of sound, 330. But it's on a flatbed truck traveling 2.7 repeating meters per second. And the frequency that we were playing was 275, the lowest possible one. We'll just go with that one. Okay. What's going to happen is the frequency is now going to change, and it'll be even lower, I guess. So the whole band is going to sound flat. 330 divided by 330 plus 2.7 repeating times by 275 gives me 272.7. So for those of you who are musically inclined, it means that if the band is coming towards you, they'll sound a little bit sharp. And if the band is going away from you, they'd sound a little bit flat. I mean, not a lot, not enough that everyone will notice. If you have a good musical ear, you might actually be able to tell the difference. So that was kind of a cool question to tie it all together. Questions? That made sense? Okay. It's one thing to watch and have me explain it to you, and you go, yeah, okay, it made sense. But you probably know where I'm going with this. You got to practice. Right? You can't just watch and go, yeah, I got it. You got to try. You got to do your reps, right? It would be like me watching someone how to throw a baseball and go, yeah, I'm sure I can do that. Well, if I actually want to get good at it, I better actually throw a baseball a few times. So, class, I've set aside the rest of today, which is about half an hour. I've got all of tomorrow, all of Thursday as work time. Here's your to-do list. It's on the board still. Number 1, if you haven't done your circular motion lab, do that first. It's the one thing that's absolutely required. You should do that first. Okay. However, for the rest of the time I've got for you here, you've got a few optional things. There's 2 different assignments that have scenarios in there for you to practice. I give you the answer keys online. I'm the kind of teacher who just politely nags you a lot. That's what I do. I don't make you do it, but I suggest over and over you should do it. So, and there's also the practice quiz. Okay, that's what I want you guys to work on over the next couple of days. Okay, on Friday we're going to talk about our research project. And then we're going to spend a week working on that research project, the research paper. We're going to do it in groups. And I'm going to help walk you through it, because it might be a little intimidating to have to write a research paper in grade 11. But my whole goal is to help you in case you do it in university. So next week, we're also going to do a practice quiz. And I'm also going to give you assignment number 3. It's going to be the one that is due for marks. It's the only one that is actually due for marks. But in the meantime, you can work on this stuff here. When you come back from May long weekend, after we come back from that weekend, that's when we're writing our unit test. Okay. And if you guys know about how the schedule works, May long weekend is on the Monday. Tuesday is also a PD day. I think I actually have the unit test being written on the Wednesday or the Thursday. So we still have 2 solid weeks before we write the unit test. So I guess I'm politely saying, start the practice, right? Ask me for help. It's going to start getting pretty busy. These next 2 weeks is the busy part of your unit, because you got all these things to work on. So the sooner you do them, the sooner you can get feedback. Sound good? Guys, you're free to work wherever you want. Please be there. please be in the location that you say you're going to be. Please be working. But you guys are free to work on and go wherever you want to. But like, stick around here if you want help. Okay. So, okay, I'm done. Hey Google, play B93.